Hey, what's up, you guys? So I'm Wish. We'll try to solve homework six problems together today. Okay, so for homework six, problem one, the question is, what is the size of a stack memory segment in kilobytes? So this question has nothing like technical about it. It's just um, reading a book and memorizing stuff. But in order to get that answer, what we can do is I'll share my screen. And I just Googled the size, and you can read on this website. It's called Geeks of Geeks. It says that a segment of a logical memory unit may be up to 64 kilobytes long. So that will be our answer for the first problem. So the size of let me broadcast my screen. Awesome. So the size of a stack segment in kilobytes is 64 kilobytes. So again, this problem has like nothing, like you don't have to do any special math or anything else. It's just basic general knowledge. Okay. The next question is, what is the problem with the following code? Push PL, push BX, push SI. Okay. So first of all these instructions look good, but we know that there is something wrong with one of those instructions. So let's see. So they're all push. Okay, so and then BL, BX, and SI. We know BL has a size is the lower 8 bits of BX, so it's 8 bits. BX is like 16-bit register. Okay, and SI is also 16-bit register. Okay, so the only difference in these three instructions is that the first instruction is 8-bit, the others are 16-bit. But okay, like the register, I mean, the first instructions register is 8 bits, the other two instructions register are 16 bits. So that's the only difference that we can see. But now we have to see how does push work in x86. So I'll just use push in x86, assembly x86. So okay, so we can read in this, if you read at this website at page, or you can just Google it. A push instruction usually works for a 16-bit or a 32-bit or a 64-bit register. So this means push will work on this register because this is 16-bit. Push will work on this register because it's 16-bit, but push will not work properly on this register because this register is only 8 bits, and push is trying to push 18 bits of the something onto the stack. So we know what push actually does, right? Push just takes whatever thing is on the registers and save it on the stack. And we know each segment in a stack is 16-bit long. So this means, a push command just takes 16 bits of data from the register to the stack. But in this case, in the first instruction, we have only 8 bits. So that's what's wrong with this whole this line of code, because we're trying to push 16 bits of data onto the stack, but the register is only 8 bits. I hope that makes sense. Okay, the next question is, if SP is 1008 after executing one push, what will be the new value of SP? Okay, so we know that push is a 16-bit command, right? It pushes 16-bit onto the register, right? And we know that one hex is 8 bits. One hex is 8 bits. So this means if we want to make it push to 16 bits, so let's say this is the memory address. Right? Each segment is 16 bits. So this means if this is the starting address and we're gonna push this onto the stack, so the pointer gonna and so we know that SP is a stack pointer register, right? that it's a stack pointer register, and we're pushing it onto the stack, like whatever the value is, we're pushing it to the stack. Okay, and we know a push is 16-bit and one hex is 8 bits, right? So what we can do is, so since we are pushing 16 bits, this means we're going to change 2 hex values. We're going to decrement, because if, let's say, if the stack pointer is pointing at this location, let's just say, right? Let's say its stack pointer is pointing at this. So we're going to push the data onto the stack, like on somewhere else in this case. So what we're going to do, we're going to move the stack pointer above. Let's say, let's just assume this is address 1, 2, 3, 4, 5. At this point, it's pointing towards location 3 in the memory. If I push, I'm going to push the stack pointer from, instead of pointing here, to point here, right? That's how push will work logically. Now, that's the logic behind how push works, right? How will push on the stack. But now the complicated part about the push. A push is a 16-bit, but one hex is 18 bits, because this is hex, right? And we know each hex digit is an 8-bit number. So like it occupies 8 bits. So this means if we have to push, which is 16-bit, and one hex is 1 bit, this means we have to move it. It has to go 2 places above in the hex. I don't know if that makes sense. Like, by pushing 1 hex value will only move 8 bits. Yeah, this is a better way of explaining it too. Yeah, sorry. So since we know that, okay, scratch everything. Let's do it again. Okay, so the stack point, let's say the stack pointer is pointing at 3, right? Let's just assume. And if I push, it's gonna start pointing towards 2, and it won't point to 1. That's how push work. And we know push is a 16-bit, like it will push 16 bits from one place to another. Okay, but we know 1 hex is an 8-bit. So this means in order to push all the 16 bits onto the stack or somewhere else, we have to decrement it twice. So this means if initially the stack pointer was pointing at 3, and I just want to move 8 bits, it will point towards here. Like, let's say they're all hex values, hex locations. If I do this, if instead of pointing 3, if I move from 3 to 2, I moved only 8 bits. But the push command moves 16 bits. So this means if I do this and scratch this, this means moving from 3 to 1, this will move 16 bits from the stack pointer. So this means our initial, we have 1008H. So if it moves to 1007H, this means it only moved 8-bit. But push is a 16. This means 1006H will be the 16-bit. This means after pushing after this command, push SP, initially the SP location was this, but after this command, the new location would be this. I hope that makes sense. Sorry, it took me a while to make it understandable. Okay. So the next question is, if SP is 1008, after executing 1 pop, what will be the value of SP? Okay, push and pop are similar. Let's say if I say push AX, that means what I'm trying to do is whatever the value in AX register is, I'm just pushing that value onto the stack. But if I do pop AX, it's similar to push, but instead of pushing the value from register to the stack, pop will do the opposite. It'll pop the value, whatever on the stack is, back onto the register, if that makes sense. So it's totally opposite. And another thing, pop is also a 16-bit. It also moves 16-bit at a time. Okay, this is hex. 1 hex is 8 bits, right? Okay, so this means if right now our SP is at 1008H, this is 1007, this is 1009H, right? If I'm popping it, this means I'm putting the value back. So this means my stack pointer will point at this location now after and if it points this means it popped 8 bits. But we know a pop is actually, it moved actually 16 bits. So I can just say 1008H. And if it points here, this means it popped 16 bits back onto the register. So since initially was 1008, this means after using the pop command, it'll add 16 bits to the current address, which was this, and 16 bits to the current address is 1008. So the answer to this will be AH. Okay, I think I'm making sense, but again, it's your first semester of computer architecture, so there might be like might be saying things that make sense to me, but it doesn't make sense to you guys. So feel free to contact me if it doesn't make sense to you. Okay, on to the next question. Okay, so next question. This question. Okay, in this question we have a stack segment, a data segment, a stack pointer, and I think it's called source index. I think SI is called source index. Okay, so basically, let's see. So a stack segment is basically a big chunk of memory, and it's called stack. Basically, that's what I can tell you. A data segment is a big chunk of memory that stores all the data and the variables in it. A stack pointer is a register that points in the stack segment so that we can know where the specific thing is located in the stack. And a source index is a pointer that points in the data segment to tell where the data is at. So this means stack segment and source stack pointer are like, stack segment is a big thing. Stack pointer is it points where in the stack segment, and data segment and source index is like, and they're related because data segment is a big chunk of memory and source index is a pointer that points where in the data segment, if that makes sense. Okay, in this case, we gotta find the physical address of the current location in the stack. Okay, we have to find the address location in the stack. So this means we don't care about data segment because we're looking in the stack. So we're gonna use this address. And we know stack pointer is the one that points addresses in the stack segment. So this means we don't care source index either. After that, it's pretty simple. We just go by a simple rule. So the address, let's say, like it's like this, right? So this is the stack segment, let's say. The address of this whole block is 400H. That's how we write it. But whenever we have to solve it, we just add another zero. It's a convention. I don't know the exact reason. I learned about it, but I forgot. So, but just remember that whenever you have a address of a stack, just add a zero after that. Okay, and this stack is divided into different memory locations. So the stack pointer will be pointing at something. Usually this, the bottom address will be 0000, and the top address will be FFFFF. Okay, that'll be the address. So it's pointing at, let's say this location 1000 is 1000, and it's pointing at this. Stack pointer is pointing at this. So what will be the physical address of this point will be, basically you're gonna take the whole address of the segment, which is 40,000, plus you're gonna add the address of the stack pointer, which is 1000. So this means the answer will be 41000. Does that make sense? Like we did this problem earlier, like in the past homework problems. So I think it makes sense. But if it doesn't, again, feel free to contact me. Okay. Again, we have a stack segment, a data segment, a stack pointer, and a source index. Cool. Find the logical address of the current location in the stack. Again, we're talking about the stack, so we can just ignore the data segment and source index. So we just have these two addresses we're going to deal with, and we're looking for the logical address. Remember, in the past problem, we were looking for the physical address, like where physically it is, like where it is. But the logical address, it's like more of a convention. Instead of like adding things together, we can just like, okay, we are kind of engineers, we are kind of lazy people. So instead of doing the addition, the logical address is more like our way. So what we basically do to find a logical address, we just write stack segment : stack pointer. That's basically it. So stack segment has an address of 4,000. Okay, and the stack pointer has an address of 1,000. So this will be the logical address of the current location of the stack. It's similar to the past problem where we find the physical address. In the physical address, we just add a 0 behind the stack segment and add the stack pointer to that address. But in this problem, when we're looking for the logical address, we just take the stack segment address. We don't add a 0 in this case. We just take it as it is, add colons, and then write stack pointer right behind it. Pretty simple, right? Okay, and the next question is, we have stack segment, we have data segment, we have stack pointer, and a source index. And we are looking in the stack. So this means we don't care about this, we don't care about this. Cool. And we'll find the lower range of the physical address, the lower range. And remember, we talked earlier, if this is the stack segment and it has this, like this is the 4,000 block of the stack segment, then it has like different memory locations in it. And the topmost memory location is always F, 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 F. And the bottom one is 0, 0, 0, 0. All right. Okay. So the lower range of and it's looking for the physical address. Remember, not the logical address. It's looking for the physical address, if that makes sense. Okay. So this means we're gonna add stuff. So we know that what we do in this case, we add source plus stack. We add pointer to the stack address. So in this case, this location is 4,000. But since we're looking for the physical address, we're gonna add another 0 behind it. Now we're gonna add what's gonna be the stack pointer. Is this gonna be the stack pointer? No, because in this case, it's asking for the lower range. What's the bottom last thing in this? In this case, the last thing in this stack is 0, 0, 0, 0. So we're gonna add 0, 0, 0, 0 because that's the lowest a stack pointer can go in this stack. Because it's like, think about it. There's a street, and the addresses go from 1 to 100 on that street. And I ask you, what's right now you live in address 23, let's say, but I'm asking you, what's the first house you can go to on the street? It'll be 1, right? So it's similar to that. Wait, I don't know if that example makes sense or not. I was just trying. But yeah, since we know that the lowest address in this stack segment is 0, 0, 0, and the highest is FFF, and it's asking what's the lower range of the physical address. Instead of using the address that's given to us, we're just gonna use the lowest one possible because it's asking us for the lower range. So I can just say when we add them together, my LB 40,000. So that'll be the lowest possible address, physical address in the stack. And the next one, it's asking us for the upper range. So it's the same problem, same everything. But in this case, instead of asking for the lower one, it's asking for the upper one. So we'll do the same thing, 40,000 plus F, 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 F. So our physical address will be 4F, F, F, F. That'll be the upper range of the physical address in the stack. So, and that's it. It was pretty quick and pretty simple, straightforward. I hope this makes sense to you guys. But if it doesn't, feel free to contact me or Professor Mustafa. And I hope you guys have a good day. Thank you. Bye.